The F-35 Lightning II was engineered with a singular objective: to render fourth-generation fighters obsolete. It was built as the solitary successor to legacy fleets. But in 2026, air forces cannot acquire enough of them to execute a fleet-wide transition. Instead, dozens of completed jets are sitting parked on the tarmac, unable to fly solo missions. The delays reached a breaking point this year. Faced with mounting failures, the U.S. Department of Defense took drastic action for fiscal year 2026, cutting U.S. Air Force F-35A procurement by nearly 45%, dropping the order from 48 airframes down to just 24. This chart visualizes the core metrics driving that decision. A single F-35A costs around $82.5 million, with a mission-capable rate near 50%. Meanwhile, a modernized F-16 costs $50 million, hitting mission-capable rates between 70 and 75%. The math is unforgiving. These numbers demonstrate an exclusive, stealth-only airspace is currently a logistical impossibility. As a result, allied nations are aggressively pivoting to a high-low mix, keeping modernized F-16s flying right alongside the F-35s. In this arrangement, the expensive stealth platform penetrates heavily contested airspace, while the cheaper legacy jets provide raw payload capacity, mass, and homeland defense. Two specific crises force this compromise: a cascading string of engineering failures stalling the assembly line, and the severe radio frequency hurdles of networking fifth- and fourth-generation jets together in the sky. The F-35 software is currently degrading its own hardware, while its pilots work to reconcile a tactical environment where stealth platforms and legacy jets cannot communicate without compromising their positions. Modern fighter jets are essentially flying supercomputers, and the F-35 relies on over 20 million lines of code to operate. Its most critical vulnerability is its own programming. The platform is currently struggling under the weight of the Technology Refresh 3 update, or TR3. This hardware and software package is the foundational requirement for the Block 4 suite, providing the processing power necessary for new weapons and advanced electronic warfare. According to the Pentagon's Director of Operational Test and Evaluation, TR3 is predominantly unusable. Throughout 2025, chronic stability deficiencies caused the core processors to routinely crash and freeze mid-flight. When those processors freeze, they create a massive data bottleneck. The stitched 360-degree visual feed from the distributed aperture system frequently fails, and the advanced AN/ASQ239 electronic warfare suite is locked out of its jamming protocols, restricted entirely to basic threat detection. Physical sensors and advanced stealth geometries offer zero tactical advantage if the underlying algorithmic logic cannot process the incoming environmental data. These processor upgrades also come with a severe physical cost. The new TR3 computing modules demand an immense increase in electrical power and cooling capacity. This diagram shows the Power and Thermal Management Subsystem, or PTMS. Its entire function is routing waste heat away from the new avionics. The PTMS has to dump this excess thermal load directly into the jet's legacy F-135 engine. This forces an engine designed over 2 decades ago to run far beyond its original thermodynamic parameters. Pushing the engine this hard accelerates wear on the hot section components, causing dangerous levels of physical degradation to the hardware itself. The Government Accountability Office estimates this accelerated wear will add $38 billion in lifecycle costs to the program. A bottleneck in digital code has triggered a cascading thermodynamic failure, physically deteriorating the very engine meant to propel the aircraft. These internal engineering strains directly paralyze the manufacturing line. Looking at the factory floor, the scale of the bottleneck becomes visible. A recent audit revealed the final assembly line is crippled by an average of 4,000 simultaneous parts shortages. The most critical missing components are the delayed TR3 hardware modules and leading-edge wing flaps. Because of these missing parts, aircraft are currently being delivered an average of 238 days behind schedule. This leaves dozens of fully assembled but completely non-functional F-35s sitting parked in Fort Worth, waiting for code and hardware to catch up. Global air forces are committing to the high-low mix out of sheer necessity. It is impossible to scale a stealth doctrine around an airframe that is suffocating its own supply chain. Even when the F-35 does make it to the flight line, operating it alongside an F-16 introduces a severe communications hurdle. They speak entirely different digital languages. This top-down map illustrates the problem. The F-16 operates on the standard Link 16 network, an omnidirectional system broadcasting radar tracks by pulsating in all directions. Broadcasting omnidirectionally is a major tactical vulnerability. Emitting those wide radio waves instantly exposes the aircraft's position to enemy sensors and breaks stealth. The F-35 avoids this by using the Multifunction Advanced Data Link, or MADL. Instead of wide circles, MADL fires tightly focused, directional energy beams between stealth nodes to maintain a low probability of intercept profile. This creates a tactical paradox. The invisible strike fighter penetrating hostile territory cannot directly share data with the heavily armed F-16s trailing behind it without giving away both of their positions. To bridge this divide, mixed squadrons use a few specific integration tactics. The simplest is called silent ingestion. During silent ingestion, the F-35 acts strictly as a passive sponge. It absorbs the older jet's radar tracks and maintains total radio silence, never transmitting a signal back. But when the stealth fighter needs to share the targeting data it gathers deep behind enemy lines, passive absorption isn't enough. They need a translator node. This requires a specialized relay aircraft, like the E-11A BACN, loitering far back in safe airspace. The stealthy F-35 fires its narrow MADL beam backward to this relay node. The relay node catches the invisible MADL data, translates the data, and blasts it out over the standard Link 16 network, so the older fourth-generation jets can receive the tactical picture. Translator nodes keep the F-35 cloaked, but tying the operation to a large, vulnerable relay plane limits how far into hostile territory the strike package can go. For deep penetration missions, squadrons use their highest-risk integration doctrine, entirely contained within the fighter group itself, the anchor tactic. In this setup, a forward package of F-35s advances deep into the threat zone. They gather targeting data and communicate strictly via MADL to remain invisible, sending that data backward. Waiting in safe airspace is a single rear F-35, acting as the squad's router. This anchor jet receives the MADL data, drops its stealth profile, and begins emitting wide Link 16 pulses to the fleet of F-16s trailing behind. The anchor intentionally paints a target on its own back, sacrificing its core defensive advantage just to pass targeting coordinates to the missile carriers. To make this multi-generational airspace function, the stealth fleet has to selectively compromise its defining architectural feature. When these complex data links actually align, the pilot experiences the ultimate technological payoff of the platform, algorithmic sensor fusion. The jet processes these disparate data feeds and stitches them into a single, unified tactical display. The F-35's software engine does the heavy lifting, cleaning up the messy, overlapping communication streams into a pristine map of the battle space. But until the TR-3 software stops crashing and the legacy engine's thermal capacity is completely redesigned, that data processing potential remains severely bottlenecked. The original dream of a completely fifth-generation, stealth-only airspace is officially suspended by the very systems meant to guarantee it. The data proves that highly advanced airframes cannot dictate the skies alone. For the foreseeable future, the 50-year-old F-16 Viper will remain the indispensable muscle behind the stealth transition.